Today we're going to look at piecewise functions. So let's look at a simple example of a piecewise function. Let's say x equals a person's age and y equals the person's height. So I'm going to make a little xy axis here, and maybe the height will have 2, 4, 6 feet here, and the age we're going to do 10, 20, 30, 40, 50, 60, 70, and 80. Now, when you're first born, you're probably 20 to 22 inches long, somewhere in there, so maybe about a little under 2 feet. And as you grow through elementary school and junior high and so forth, you're growing. And you might even have a kind of a growth spurt. So let's say this is a male, and he has a big growth spurt maybe in his late teenage years. And then he just kind of levels off and stays the same height most of his life until maybe he gets to be close to 80, and maybe he loses just a few inches in height because his bones are starting to settle, losing some bone density and so forth. Now, this is one function because each age corresponds to one height, but I can't write one algebraic rule for this entire function because the different parts of the graph behave differently. This looks like it could maybe be something like an exponential function. This looks like it's just a constant linear function, and this is a decreasing maybe linear function. So I have maybe 3 different function rules for the different parts of this graph. I might even have more than one function rule for the increasing part of the graph if it isn't a smooth curve. So this is an example of where different sections of the domain might have different rules for the relationship with y. If we look at this function right here, you can see f of x equals x minus 1, 1/2 x squared, or 2x minus 11. 3 different function rules. So these are the rules for the function, and on this side are the parts of the domain that go with each rule. So, for example, if we look at the first line, when x is less than -2, f of x is equal to x minus 1. So for any values where x is less than -2, I will use the rule x minus 1 to find the y value. But when x is from -2 to 3, then I'm going to use this rule, 1/2 x squared. And when x is from 4 to 6, I'll use 2x minus 11. So we have different function rules for different parts of the domain. Different function rules for different parts of the domain. Now let's evaluate several function values. So if you look over here, evaluate the function f of -1. Remember, that means when x is -1, what is y? Well, if x is -1, I have to first look at which section of the domain that fits in. Well, -1 is between -2 and 3, so that means I'm going to be using rule number 2 to evaluate this particular value of x. So this f of -1 is going to be 1/2 times -1 squared, which is 1/2 times +1, or 1/2. So that means -1, 1/2 is a point on the function. When x is 4, I'm going to have to go to rule number 3 because 4 is in the section of the domain right here where x is greater than or equal to 4 and less than 6. So I have to use number 3 for this one and say that y is going to be 2 times 4 minus 11, which is -3. So that means the point 4, -3 is on the graph. Now if I want to evaluate x equals 7 and I go over here to look, I see that 7 doesn't fit in any of these 3 sections of the domain. In fact, 7 is not in the domain. So 7 is not in the domain, therefore there is no y value associated with x equals 7. Now if I want to graph this function, I have to make a table of values for 3 separate functions. And I know in the past you've often done that when you've graphed a function, a linear quadratic function or something, or any new type of function especially, you make a table of values and plot points. So what we're going to do is split this in 3 ways. I'm going to actually color code these to make it easier. So we're going to call the first line number 1 here, and the second line, which I'll do in red, that'll be number 2, and the third line, which I'm going to do in black, is number 3. So I'm going to make a table of values for each one of those. So for number 1, where f of x equals x minus 1, I'm going to make a table of values that includes -2 and below. Now you might think, well, why am I including -2? Because x is less than -2. Well, remember, x is any value up to -2, like -1.99, -1.98, -1.5, any of those values. So if I start at -3, I'm sorry, not -1.99, like -2.01, for example, would be less than -2, or -2.05, or -2.5. If I start at -3, I'll miss that section that's in between -3 and -2. So I have to have my starting endpoint in my table to be -2, and then pick values less than -2, like -3 and -4. Recognizing that this is going to be an open circle and everything to the left, or everything smaller, so I'm going to put an open circle and realize I'm going to do everything less than that. And when I put this on the graph, I will have to put an open circle here because it's not included in this part of the domain. So when I put -2 minus 1, I get -3, -3 minus 1, -4, -4 minus 1 is -5. So plotting these points, -2, -3 on the graph, open endpoint, -3, -4, -4, -5, and so forth. And I keep on going with this graph. It goes on forever, this section of the graph. Number 2 has the function f of x is equal to 1/2 x squared. And this is for values from -2 to 3, and -2 and 3 are both included in this section of the domain as endpoints because they are both equal to x as well as less than or greater than. So when I set up my table here, I'm going to go all the way from -2 to 3. -2, -1, 0, 1, 2, 3. I'm going to have to write a little smaller here. I'm going to substitute each value in for x, square it, and then multiply it by 1/2. So -2 squared is 4 times 1/2 is 2. -1 squared is 1 times 1/2 is 1/2. Then I get 0 when I substitute 0, 1/2 when I substitute 1, 2 when I substitute 2, and then when putting in 3, 3 squared is 9, 1/2 of 9 is 4.5. So plotting these points, remember, closed endpoints on both ends and then all the points in between. So -2, 2, -1, 1/2, 0, 0, 1, 1/2, 2, 2, and 3, 4.5. Now this is an x squared function, so it should look like a piece of a parabola. And it does indeed look like a piece of a parabola. Do not extend past those 2 endpoints and put arrows on, because this graph does not go anywhere, this section of the graph does not go anywhere except for between -2 and 3 on the x-axis. If I extended it, for example, if I extended the graph to the left, then I would have a situation where I would have 2 different y values for the same x value. So we can't do that. Section number 3 is where f of x is equal to 2x minus 11. So I have x and f of x, and this is for the section of the graph that's from 4 to 6, but not including 6. So 4, 5, 6. 4 is a closed endpoint, 6 is an open endpoint. Substituting 4 in for x, I get 8 minus 11 is 3, 10 minus 11, -1, and 12 minus 11 is 1. So I have a point at 4, -3, a point at 5, 1, and or 5, negative 1, and a point at 6, 1 with an open circle for that point. And so there's this little section of the graph, just a little line segment. All right, so let's take a look now at domain and range of this function. Remember, for domain, we have to look to the left and to the right and see how far x goes in both directions. So if we look to the left, we see that there's this arrow going down and to the left. So we can see that the domain continues on to infinity in this direction, or I should say to negative infinity. Now, if we look at the part of the graph here, we see that we have x values from negative 5, negative 4, negative 3, but when we get to negative 2, there is no x value that there is no point for negative 2 down here on the blue section of the graph. But if we go up to the red section of the graph, there is a point that has an x-coordinate of negative 2. And then these points have x-coordinates of negative 1, 0, 1, 2, and 3. And so I've gone so far all the way to 3. But if I try to find something in between negative 3 and 4, there is nothing on the graph between negative 3 and 4. So I've come to a stopping point when I get to 3. So my graph goes all the way to where x is, or should say my domain goes all the way to where x is 3. Then it picks up again when x is 4. So there's a point when x is 4, and it goes until x is 6, but does not include 6. So the domain is in two sections, negative infinity to 3, or 4 to 6. Remember, this means or. So there's really only one gap in the domain is right here, because I can always find from anywhere from negative infinity to 3, I can find a point on the graph that has an x value in that interval. There's just no x values that have any points on the graph between 3 and 4. Now let's look at the range. Remember, with range, now we're looking on the graph up and down to see how far down we can go and how far up, and see if there's any gaps in y values. So we can see with this downward arrow that negative infinity is going to be my low value for my range. So I'm going to go ahead and put negative infinity here. And now let's take a look at y values. So this section of the graph includes y values up until I get to negative 2 here. I'm sorry. Yeah, up till I get to negative 2. But there's no y value here because that's not a point. But if I go across here, I find, oh, there's a y value for negative 2 over here. And then this graph goes up to where I get to y equals 1, but there's really no point here. But if I go over to the red graph, that picks up and I have more y values here for negative, or for 1, 2, 3, 4, up to 4.5. So basically, if I were to draw horizontal lines anywhere on the graph between negative infinity and positive 4.5, any horizontal line I drew would hit somewhere on the graph and I would have a y value represented. Now realize there's going to be several places where I'm going to hit two different y values with a horizontal line, but that's okay. I can have a y value with two different x values. I just can't have an x value with two different y values. This is still a function. So I can go all the way up to 4.5, and every point, every y value between those two is included somewhere on the graph. So this is negative infinity to 4.5. Close this with a square bracket. Now, one other little definition to mention for a piecewise function is what's called a discontinuity. A discontinuity is a break in the graph, and you can see we have two breaks in the graph, a break between the blue section and the red section, and between the red section and the black section. But how do we describe those breaks? Breaks in the graph are x values at which you pick up your pencil when you're drawing along the graph. So let's make a little pencil here. So here's my little pencil. So I'm drawing the graph, I get to this point and I have to pick up my pencil and move it over here. So there's a break in the graph at x equals negative 2. And then I've got my pencil, I'm drawing along, and then I have to pick up my pencil and move it down here. So there's another break in the graph when x equals 3. So I'm going to say at x equals -2, I should probably say and x equals 3. And it doesn't jump right down to a point on the graph. We have to kind of jump over to where x equals 4. So I'm just going to put it starts again at x equals 4. So kind of just to add a little more information about that second break in the graph. So those are known as discontinuities. And this is why we're learning some of these terms, is all of these characteristics of functions, domain, range, discontinuity, and so forth, are all things that are very significant when you're analyzing functions and doing calculus, because certain types of discontinuities cause you to have to change what you do in calculus. So I want you to be familiar with these terms. That, of course, is why the course is called pre-calculus. In addition to lots of interesting math that you're going to be learning, you're also preparing for calculus should you decide to take that. Okay, one more example, and this is how do we actually write a piecewise function for a graph? So let's go ahead and look at this graph, and we're going to realize it's in 3 sections, so it's going to have 3 different function rules. So I'm going to open up a curly bracket and make a space for 3 different function rules, each with its own domain. So we're going to start by looking at the domains for each section of the graph. So I'm going to number the sections of the graph: section number 1, section number 2, and section number 3. And I'm going to just kind of put it out here so it's sort of out of the way, because I'm going to need to do some things with that section number 3. Section number 1, it applies for x values that are -2 and lower. So this whole section of the graph is -2 and lower. So I'm going to say x is less than or equal to -2. There's a closed circle here, so the -2 is included in this section. The middle section of the graph goes from where x is -2, and I think I'm going to circle these here, to where x is +3. So where x is +3. So we're in between these two values here. Here I was at -2 and less, and now I'm in between -2 and -3, but open circles here, so neither of those values is included in the interval. So I'm going to say -2 is less than x is less than 3. The third section is for values of 3 and greater. So this is x is greater than or equal to 3. Now, I put all of these, I did not use interval notation for these intervals. If you are more comfortable at this point with interval notation and you want to say -∞ to -2 square bracket, curved bracket -2 comma 3 curved bracket, and square bracket 3 comma +∞ curved bracket, you can do that if you want to. Typically you do see the inequalities used in piecewise notation, but I would be okay if you wanted to use interval notation. Alright, so let's look at the first section of the graph. So equation number 1. Equation number 1 is just a horizontal line. This is the line y equals 3. Or we could say f of x equals 3, because f of x is y. Notice that in piecewise notation, the equal sign and the f of x are already written. So right here, I don't have an equal sign. I just write the number 3. So whenever you see a single constant number used as a function rule, it means you're going to have a horizontal line. The middle section of the graph is an absolute value graph. And so just to make things easier on you, because I think writing the equation of a piecewise function is a challenging thing as it is, the only functions I'm going to be giving you when I ask you to write a piecewise function are linear functions, a really basic absolute value function that looks exactly like this, or a really basic quadratic function, f of x equals x squared. So those, I'm going to stick to those 3 functions. So the middle section, equation number 2, is just an absolute value graph. So there's the function rule for number 2. And notice in an absolute value graph goes through 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. It's an even function, as you note right there. Okay, equation number 3 is a line. And after having Algebra 1 and Algebra 2, you've done some extensive study of lines. So I'm going to go through this pretty quickly. Hopefully you remember all of what to do with an equation of a line. An equation of a line, the basic equation is y equals mx plus b, where m is slope and b is y-intercept. There's 2 ways to find slope. One way would be to take the coordinates of these 2 points, subtract the y values, y2 minus y1 over x2 minus x1. So you can do that. So we could say m is y2 minus y1 over x2 minus x1. But I'm not going to do that way because it's really simple to read this off the graph. I can just recognize that in going from the point 3, negative 1 to the point 4, negative 3, I'm going down 2 in the y direction and up 1 in the x direction. So the slope is, the change in y direction is negative 2 and the change in my 2 x's is positive 1. So my slope is negative 2. So that means negative 2 is going to go right here in the equation as the coefficient of the x variable. Now to find y-intercept, which is b, I have to do one of 2 things. I'm going to show you the first way because this will always work. The other way only sometimes works. I need to pick a point that's on the graph. So I'm going to pick this point 4, negative 3. And I'm going to use 4, negative 3 as my x and y values in my equation. So 4 is x, negative 3 is y, and I'm going to write the equation with the slope in there for negative 2 in for slope, with 4 in for x, and negative 3 in for y. So when I do that, I'll do this in blue, negative 3 is equal to negative 2 times 4 plus b. This allows me to figure out what the y-intercept has to be to make the equation true. So this is negative 3 plus equal, or not plus, negative 3 equals negative 8 plus b, which means b has to be 5. So that means the y-intercept is 5. So if I know b is 5 and I know m is negative 2, I have the equation negative 2x plus 5. I can double check my equation by substituting another point in. So I have the point 3, negative 1. If I put 3 for x, 3 times negative 2 is negative 6, plus 5 is negative 1. So that works. Now the other way that you can find y-intercept, depending on if it's a nice number and if the graph is big enough to show, is I could just continue the pattern of the slope from and extend the line until it crosses the y-axis. So if I go to the left here, I would go left 1 up 2, left 1 up 2, left 1 up 2, left 1 up 2, and look, I would end up right here at 5 on the x-axis if I extended the line. Or sorry, 5 on the y-axis, which shows me that my y-intercept is 5. So that is the equation of the piecewise function.